Yes.
So when should I stop? Should I stop noon? No. Okay. So today I want to introduce the Fargues content curve and speak a little bit about vector bundles Fargues content curve. So this lecture will be more sketchy than the last one. Unfortunately, I will not be able to really explain things. But yeah, let me try still. So recall last time what we did. We saw that okay, there is this general notion of a Fourier ring, Fourier pairs, and what we discussed last time was how to attach to it something called star AA plus, which is called an affine space. So the underlying topological space so as I said, it's described by the equivalence classes of continuous variation A, which take a value less than or equal to 1 and A plus. The underlying topological space is spectral. And on the topological space, we define the sheaf of topological rings. These, also the variant with the plus, by using rational subsets. So that's what we did last time. As I explained, also like any discrete ring or any p-adic ring for a finitely generated ideal of definition give rise to a Hoover pair. If you just take A plus to be A. So in particular, Hoover theory somehow includes also the theory of schemes or formal schemes. But the class of p-adic spaces we will be interested in these lectures is kind of orthogonal to this. So we also saw that you can define notion of space pair, and so the analytic, the p-adic spaces we will consider are the ones which are said to be analytic. So it's analytic space. So okay, first of all, this is, as I mentioned at the end of the lecture, this is usually not always a sheaf, but I decided to completely ignore this issue and pretend this is always sheafy. And okay, then you define general p-adic spaces by gluing this affine p-adic space. But the one we will consider are the analytic ones. So it's analytic space which is locally of the form star AA plus, where A is the state tree. So it's a particular class of Fourier rings for which there exists topologically nilpotent units for the uniformizer.
Could you write bigger?
Yes.
Thank you.
Okay, and so the fact that the underlying topological space is spectral, or the fact that like discrete rings define Hoover pair, should not let you believe that this object, these analytic spaces behave like schemes. Even if abstractly the underlying topological space is the spec of some ring, they behave quite differently, and we saw some examples of this. So let me just recall 2 points. I think the first one we discussed, but maybe not the second one. So if X is an analytic space, generalizations of the points. So all points which specialize to the given point, that is all points which closure contain the given point, form totally other. So all the generalizations are, like I introduced, this notion of horizontal and vertical specializations versus generalization. And in this analytic setting, the only kind of specializations you see are the vertical ones. Of course, it is very different from the scheme case where whenever you are in dimension, say, bigger than 1, you have many irreducible components passing through points, and so many points specializing to each, which are not specializing to each other. And this is also a phenomenon we saw in this example of the affine unities. That with type 2 points, the only specialization relation were type 2 points specializing to type 5 points. Another funny thing which happened for analytical spaces is that if X point of X, and if you pick a pseudo-uniformizer, exists locally on X, then if you look at the local ring at X, I mean the first version, and its image in the residue field at X, they actually agree after p-adic completion. So since the spectra do not see the difference between the ring and its completion, this really tells you that this the point defined by X is really in this world, in this analytic world, is really the inverse limit of the rational substance which contains this point. Behavior which is reasonable if you try to do some kind of analytic geometry, but which is maybe a bit surprising from this. And so there are many arguments in p-adic geometry which are reductions to the case of non-Archimedean fields. So this is the valuation ring inside the residue field at X, which is non-Archimedean because X is analytic. And because of this observation, you can often reduce some statements to the case to description for fields. Whereas in general, in algebraic geometry, you just have to deal with local rings. So this was basically what we did last week. And now I want to give more examples of such spaces. The most important one for us will be the part content curve, but I start with some easier examples. So there is one we already saw, which is the curve P. So I take the version which makes one over D. So it's part of Z bracket T, Z bracket T, equal to the topology. So associated, it represents it represents mapping some given ID space to this, saying where the element T is. And so in particular space, and if I take K to be, say, complete, non-Archimedean field, and if I base on my use, there's no plus, not. Oh yes, thanks. Thank you. Because T has to be bounded by 1 because of this. Here I choose the A plus, I choose this simple. Because the condition of variation of T must be bounded by 1. And variation D. So whenever I write just one element, it means that I take A and A plus to be the same. Star K not. Well, this just becomes the example we discussed in length last time. So the closing immediate. Okay. Okay. Another example is p-adic line. So it's almost the same as before, but now I will just change the A plus. So instead of VT, I put, okay, I stick with my definition of over pair exponential. Okay. The integral closure of Z inside Z bracket T to have something with the integral close as required. But that doesn't matter. This condition is really just the evaluation. Eventually, no condition on the evaluation time. And this one represents the shift, the structure shift in time, because I wrote the condition evaluation. And when you, again, if K is as before, complete non-Archimedean, then the base term, I can tell you happen, but the base term of A1 to K is now isomorphic to well, the adic space, sorry, the adic line over K, which is anything in union over N of the disk of radius P to Z. So alpha is an uniformizer in K. It's increasing union of balls of like radius going to plus infinity. And as you expect, the time over K. So this type of products of adic spaces are you can like two guys after the compact, but when you take the product you get is non-affine adic space. Okay, actually, so this. So first of all, you see that all the points from like going to this to A1 is really just moving to A plus. Again, illustration of why this A plus is actually an important variable of story. So D will be contained inside A1. So let me again walk along and as if I can the non-Archimedean field, then is containing A1, K, it's open, and the closure of the line topological space inside A1 of K is just this. If I add this specialization we discussed last week, which I think I noted like this, if I remember well. So this is around 2 points. So there was this picture around each on 2 points, you have a bunch of 5 points, which are like, and when you look at the closure of the type 2 point, it looks like P1 over the residual field. It's a homomorphic field. Except at the Gauss point, where there was this point which sent T to something which is infinitely bigger than 1 and infinitely close to it. And now, when you so it open inside it, and there is one meeting point in the closure, which is
so this is so you call this is the fine.
Yes, sorry. Yeah, as before, I will be not this page.
E bar K is it star K T like
Yeah, I can write it. So this closure is star K T, and then you take the smallest possible open integral closed ring. So it's like it's again affinoid, but it's not the kind of adic spaces you see in usual. These are like perfectly fine, like usual kind of adic spaces that you see in rigid geometry, but not this. Okay. One more example before getting to the curve. The case of the open unities. Unities, because the radius is 1. The thing you get by looking at, so to indicate it's open, I will put a little interpolate. So it's defined to be the adic spectrum of EP, double brackets with the p-adic topology. And again, if you base jump to a complete non-Archimedean field, it seems like it only happens, but again, it won't be affinoid. So instead, this is I'm including union again of t, but no of t of radius. I think it's more than 1 going to 1. So, what do we want to say? Like this. So it's an increasing union of all affinities over K, which are radius less than 1. Again, I'm using spaces. And the fact it's not affinoid is based on is related to something we saw last time. Meaning that if you look at say K just Qt, if you look at VP double bracket C, and if you want to invert P, which is what they're doing by based on the point, you have to you could imagine a theory that what you get to be sparse VP double bracket T with P inverted. But it is not a Hoover ring. So it's why this condition that we had when we work with our rational subset of the elements which we try to, the family you consider to generate an open idea is important, because this is what ensures that on this localization you get you have the structure of Hoover. Here the problem comes from the fact that the family which defines the topology and DP double bracket T, you consider the p-adic topology, and you try to invert this. Okay. And now the Fargues content curve. So for this, I will fix a local field. And Q. And I fix a uniformizer phi. So local field, so this first means that there are basically two possibilities. Either we are in mixed or equal characteristics. So either E is something which is the finite extension QP, or E can be a field of Lorentz in the variable phi over the phi. I will also fix RR plus the text pair over F. State bringing characteristic E. And well, what we would like to do, for reasons want to try to explain is we would like to be able to make sense to define something like the fiber product of spar E naught with, okay, let me write S for the stated adic space. We would like to be able to define something like the fiber product of S with adic spectrum of E over the base. And but this, of course, apparently it doesn't make sense because in this situation, E is in characteristic 0, so it doesn't kill over H. However, we can give a, first, you can at least try to give a meaning to it when E is a positive characteristic. There it's quite reasonable.
Sure. Could you say why we would like to define such an object? If it's annoying, don't bother.
No, maybe let me do it later. I could try to give some motivation, like training local Langlands and how we respect I thought naively by just like working with those party. And yeah, define some kind of like crystals, geometrization of the presentation of the book on why it's enough and why you need to allow parameter, which has to be taken in the category of analytical specific characters. Yeah, it's a bit unmotivated what I'm doing now, but I hope that we more clear later why we want to do this. But as I want to say now, it's reasonable. We can do it in P. So in the case where E is of the form, we are, if we just boil down to this example we just discussed, namely, okay, so what you have is that if you look at spar OE as E naught, so E naught times LQ times spar R plus, then this identifies with the adic spectrum because E naught is just 4 series in the variable pi with the p-adic topology. You can see that in fact this is just spar R plus Laurent series with coefficients in R plus, sorry, power series with coefficients in R plus in the variable pi, endowed with this ring is endowed with the pi var p-adic topology, where var pi is a fixed pseudo-uniformizer. And now what you want to do to go from this object to the one we are interested in. So now you want to replace par E naught by generic fiber. And here similarly, you want to replace par R plus by par R plus. So what you have to do is you have to you want to impose the condition that both pi and this pseudo-uniformizer var pi becomes invertible in this adic space you want to construct. So you can set, and this adic space we want, we will call it YSE. And you define it to be this thing. To which you remove the methods where both, sorry, where one either P or var pi vanishes. So this won't be affine anymore. And in fact, this identifies with the open disk over this p-adic space S. So a version of this where instead of base changing to K, the base change to S, to which I remove the origin.
So in the spa, should the fancy pi be a pi?
So,
In the spa, is the fancy pi a pi? Or you have spa R plus?
yes. So R pi belongs to this string R plus.
Yes.
It's a pseudo-uniformizer.
Yes, but pi doesn't.
But pi
It's a
doesn't.
table, I'm sure.
Okay, I'm sorry. Yeah, so it's built in the variable pi, if you want. And you requiring that base changing from spa E naught to spa E is like imposing the condition that pi does not vanish. So in other words, that you remove the origin of the this, and then you also want that base change from spa R plus to S, and this is also forcing the thing to become inverted. And this corresponds to taking the opposite. Okay, so this is a perfectly reasonable object that we can define. And the trick in general, so back to the general case, what you do is you will not try to define the static space in general for any such state pair, but you use the following observations. Recall that if A is perfect FQ algebra, then there is a unique up to isomorphism, there is a unique way to lift A to characteristic 0, so a weight lift which lives over OE and which is flat. Has no pi torsion. Also p-adically complete. And we satisfy that A tilde mod pi is isomorphic to A. So a way to define it is to take A tilde to be the ramified bit vectors of A. So you take the bit vectors of A, behave reasonably well because A is perfect, and then you take the tensor product over the degree Q and ramified extension to P and bring integers inside it with OE is also the same as the base which from one equation, it's a ring of integers. It's also the same for our bounded cell in E. Yeah. So, yeah. If OE was characteristic T, so in this case, what you are actually doing is just the same as taking A, taking power series in E in characteristic P. Well, this A tilde will just be. So this is exactly what, if I take A to be R plus, this is exactly what appears. And so in general, you use this observation. So you restrict to the case where the state pair you consider is such that R is perfect. So for R plus state with R perfect, you define YST to be part of this A tilde. So short notation for this is just W E A. R plus A is taken to be R plus. And you remove the locus where both where either pi or, okay, now you have to do something slightly different as we did before, namely, that pi is still pseudo-uniformizer of R, but does not define an element in this ring here, right? But you have this so-called rotational lift, which is a multiplicative map from A to here, and you can just use it to send this pseudo-uniformizer to an element. So this ring will be endowed with as before, exactly as before, this pi times of p-adic topology. So you get some huge affinitic space, and you remove something to it, so that now it's not affinoid anymore, but it can be written as an increasing union of affinoid space. This is not so far from the curve yet, but no.
Sorry, I have to ask though.
Yeah.
So with R is state, does that imply then that R plus is state?
No, so R state means that there exists.
Oh, sorry, I just said the wrong word. If R is perfect, does that imply that R plus is perfect?
Okay, so yeah, I guess because R plus is assumed to be integrally closed, right? Yes. Frobenius with Frobenius. So maybe I should recall. Perfect means that Frobenius is an isomorph.
What is the statement then that R is perfect if and only if R plus is perfect? Because I mean, why else would you not say R plus is perfect?
If and only if, so. Yeah, I guess it's just yeah. I mean, recall also that in the Tate case, R is just obtained by hierarchy. And this to the uniform. I mean, a priori Tate rings are defined as just Huber rings, such as they exist to the uniformizer, but a posteriori we saw that. In fact, in this case, well, the topology on any ring of definition is just r-p-adic topology for any choice of pseudo-uniformizer, and R is obtained by inverting this pseudo-uniformizer.
In this discussion, is
well, no, it makes sense in general, so it can be both. But if OE is positive characteristic, what we are doing is just what we have done above. Yeah. So literally, if E is every characteristic, this YSE that I define is just the punctual open disk over the base S. In mixed characteristic, it's more complicated, but you can imagine by analogy with what happens in the triple characteristic situation that it's some kind of open unit disk, a punctual open unit disk, where the variable on the disk is P, pi. So P, for example, if E is P. Yeah, because this is what was happening in this positive characteristic. Okay, I'm going to have an action of some operator for Frobenius. So
There's no map back.
there is, yeah. So this lift over span. This is naturally this is an analytical space over span E. Right?
E or E0?
Ah, well, yeah, okay, E0.
Yes.
Yeah. But yeah, Justin is right. It has no map to S. This has a map to S if E has positive characteristics, as we said, just this cover. But be careful that the mental picture I gave with this analogy with open disk is not literally correct. One illustration of this is the fact that it does not fit over. Because I mean, this is something which gives but is not zero. In other words, this is not an algebra morphism. Okay, so you have a Frobenius acting on the p-adic space. So how does it look like? What's the action of this thing on functions if it's depending? So any elements in this ramified in this ring of ramified vectors can be written as in the following form: general factor of these vectors, where an belongs to R plus or n. Frobenius graph is just taking Q's power on the stationary line. Okay, one needs to check that this extends. In theory, I'm just defining phi s on here, and then you actually check that it extends to all functions on that space. And I claim that it acts freely, properly, discontinuously on YSE. Hence, you can, and I won't really justify this, but therefore you can define the Fargues-Scholze curve of E over S X at E to be the quotient of this transaction of groups. So, like in this picture with the heat, the point of this, which is what YSE looks like, at least in the equal characteristic, like the Frobenius is increasing the radius, so it's the other way around. I keep forgetting. I think it sends the disk of radius r, where r is between 0 and 1, to the disk of radius. Okay, either r to the q or r1 to the q. So you can imagine that somehow, okay, like if you take this quotient by Frobenius, what you are doing is somehow you take some sufficiently big annulus inside the open disk, such that here you have some radius, let's say r and r1 over q. And what you do is somehow you define x at e by taking the affinoid annulus and gluing along Frobenius. Frobenius different isomorphism between sectors and use them together. Okay. Like it looks like you get this Fargues-Scholze curve, which is okay. So I say that I call it the Fargues-Scholze curve for E over S, so the same case as before applied. It does not literally live over an space over phi enough. And no, even in equicharacteristic, it won't live over S because I'm modeled by the radius of S.
At least analytic area space.
This is an analytical space. Yeah, anything which lives over an Archimedean sheet. Because yeah, I mean the information here is to the information in anything over. So it's some kind of, again, quotation mark, it's some kind of compact p-adic remnants of this which behaves at least from the arithmetic point of view like all the arithmetic of spa E can be read on the object, and they have the same kind of behavior. We will see an illustration of this very soon. But the big advantage of the Fargues-Scholze curve, okay, it's clear when I say this, I didn't take the let's say as the part is enough where P is complete algebraic. Otherwise, I have some kind of family of index by S. But when S is just a geometric point, this is the curve in the sense that it's an adic space of full dimension 1, which contains a lot of information about the arithmetic of E, but still, I mean, you can do some interesting geometry comparing to this. This is more the purpose of this picture, you know, idea how that works in practice. So this is a long story which I summarize. So the way Fargues-Scholze discovered this curve is not like this. They first defined the curve as a scheme actually. The special case where S is just a geometric point, or more generally any particular scheme. They define it as a scheme, so as a part of some gradient algebra. And later on, they realized that you can also naturally define some adic space in this way. And that the construction, in fact, makes sense for in families. That you can, instead of just having S to be the adic spectrum of the field, you can take any adic space of this form. The adic spectrum of R plus, where R perfect. In fact, the construction is blue, so yeah, whenever S is an adic space locally of this form, and you can still define it as a spectrum. Okay, so so I wanted to know to say briefly something about perfect grid spaces. And because I want to explain one the relations between the theory of perfect grid spaces on this object. So that would be very brief, of course. I just want to say what the perfect grid space is. They made sense about that. So is that visible? So perfect degree is there are various definitions in the literature of perfect degree. For me, it assumed to be safe, which is always the case, which is complete, and with various conditions. So the first one are technical conditions, and the last one is important. So first of all, we want that there exists a pseudo-uniformizer of R which divides this power divides P in R naught. I also want to require that the topology used, the topology of R on R naught, is the Varpaet topology. And finally, I also want that the Frobenius map, so raising an element to its P power, from R naught mod P to R naught mod P is sorted. Okay, so as I said, the two conditions are technical conditions, which you can kind of forget. The important condition is this one. It says that at least when you go mode P, in mathematical doing, you can extract lots of T power strings. This condition is there somehow to at least say when R is a non-Archimedean field, you want to get rid of, you don't want QP, for example, to be a perfect field. So, although mode P, QP is just FT, and which will use mesomorphism, and we put this condition in order to make sure that you're only considering non-Archimedean the non-strict variation. So I will give some examples. And this is the technical condition which is the uniform with the literature. So really the important point is this one. And so to any such, you can well, so this claim that you can then define what a perfect space is, and this would be an magic space, which is locally of the form R plus R plus the space there with R perfectly. So I mean, this definition is only the second part of the definition is only reasonable because perfect spaces are which follows from the theorem I will get next. Since I decided to just ignore issues everywhere. So some examples of perfect ring are well, you can take something like P, or more generally, like any complete algebraically closed Archimedean field. If you want an example in characteristic P, which is again a field, you can take FQ double parenthesis C 1 over P infinity, which is, I mean, that means that you add all fractional powers of P, and then you take the state completion and inverse. Another example, which is not a field, you can also, like whenever you have such a base, in case that a field, like CP or the one you have before, you can take out something like say T1 T1 here now after variables. So this could be the analog of the linear functions on the closed unit disk of dimension n, but it's not perfectly dynamic. We are very practical system of rules of the coordinates and they're raising to the piece power. So another class of examples, in fact, in characteristic P. So what happens? So if R is a tight ring which leads over Fp, then R being perfect ring is in fact equivalent to R being perfect. So probability non-isomorphism. So you see that the kind of rings for which, pairs for which we were able to define this Fargues-Scholze curve were in fact exactly doing more, were exactly perfect spaces over space. Okay. So this were introduced by Scholze. This class of ring is interesting because you can sometimes go from characteristic 0 to characteristic P using the following recipe originally due to Banach, I guess, which in the terminology is called in construction. So R is a vertical ring. You can do the following: you let R flat be the inverse limit over the morphism X goes to X to the P. I don't want to call Frobenius if R is not assumed to be living in characteristics. So, okay, well, this is a priori just a monoid. So you can define the level addition on it, which makes it, so in fact, this inverse limit is the same, and we prove to be the same as inverse limit over Frobenius of you can also define R V naught. And this one actually identifies with an inverse limit over Frobenius of the same thing mod P. Now this description really gives you the ring structure on this. So the point is that this construction allows you to attach to any perpetuate ring a new, it's again, no, it's you see that this one will be living in characteristic P. So notice the perpetuate ring in characteristic P that you get. In other words, it's perfect ring. So this is the so-called tilting construction. And repeat, it allows you to attach to any perpetuate ring, whatever characteristic it has, a perpetuate ring in characteristic. What Scholze prove about this thing is the following theorem in two parts. So, if you take R plus a perpetuate pair, so take pair with R perpetuate, and you look at its tilt R flat plus. Okay, then you can attach to these two to affine spaces, which we call T and X flat. And there is a natural map between them, which is defined as follows. So recall that the points of this space correspond to valuation. So you have a certain valuation X in X, and you want to send it. I claim that there is a map. So I want to define a new valuation. It will be an element of X flat, so it should be a continuous valuation of R flat, bounded by 1 and R flat plus. And the way you do it is by decreasing that X flat sends F in R flat to R. So there is a natural map, which is the first projection from R flat to R. Not an algebra map, but there is a map. And this is denoted with sharp. So if I have F in here, I can project it to its first component. I get an element of R, and now it makes sense to apply to it the valuation defined by X. So I claim that since I did not prove anything about this construction, believe me that this defines a continuous valuation on R flat. And in fact, so this is very nice because it map induces from X to X flat, induces on a homeomorphism between the underlying topological spaces. it has the property that it identifies rational subset. So it induces a bijection between the open subset corresponding to this rational subset produced last time. But even better, if you is a rational subset which corresponds to another rational subset on inside X flat, well, it is what you expect it to be. Namely, if you so U can be written as spa of OX U OX plus U. I mean, we proved discussed last time the fact that U is automatically itself an affine space, and we define the supersheet in a way, such a way that this equality holds true. But then the claim is that U flat is just what you obtain by this. Okay, these are again perfectly rings claim, which is again perfectly fair, and so you can fix it. And corresponding p-adic space is the rational subset corresponding via this bijection to in fact, it's even better than that. It's just to prove that not only the topological spaces agree, but of course the adic spaces themselves have no chance to be isomorphic. One has a specific characteristic here, and the other not necessarily a theory. But at least the underlying topological spaces are the same, and even better, you have an identification of the data. So this is very powerful because lots of questions can be reduced to analogous questions in characteristics. And the second part of the theorem is that you have tilting, the tilting factor, it induces an equivalence between the category of all perfectoid space in. Okay, so let me fix any perfectoid space. And perfectoid spaces which live over X with a map to X are actually equivalent to perfectoid spaces over X path, just by filtering. So this is what I will refer to in the rest of the lecture as I need to use it as a tilting equivalent. Yeah, so the way this is also this fact that Schulze proves are like also what you need to use to check that you have a nice that any perfectoid rings gives rise to nice shifty adic spaces. And after you have done this, you go on to prove this equivalence, but from a formulation of it known as the almost purity theorem, and this is later what allows you to actually improve this topological statement on equivalence. And the argument is an instance of, and part of the argument is an instance of what I was saying at the beginning. It's a situation where the proof of the key statement is actually reduced to fit by using this fact. You can actually write points as inverse limits of rational systems. So you first prove results about perfectly fit, and then you use shiftiness and geometry to prove statements about more general perfectly fit. Okay, and the reason I wanted to state this theorem is, well, I may need it later, but it also gives the point of view on the Fargues-Scholze curve. namely, the statement is the following. So let S over FQ be a perfect space. There is a one-to-one correspondence between on the one hand, empty of S over E. So E is as in the description of the part content representation locality, which that is perfectly spaces S sharp over E. So this no are S was giving in characteristic P, but no this empty is a perfect space which lives over the PP, which may be of characteristic 0. But an isomorphism between the T of S sharp and S. So that's why these objects are called untipped, because these are perfect space which tip to the given perfect space. And these are the same as morphisms. From S sharp to the static space YFP over. And in fact, even better than that, like that, that S sharp. This is S sharp, yes.
I don't understand this thing.
Should it be S?
So didn't fix S sharp. Sorry, what do I sorry, what do you want to say?
Is that calling you on to this?
What?
How can that be a bijection
Yeah,
between
sorry, what do I want to say? Maybe I want to say sections. Of the projection now. Okay, let me see. We take okay. Let me say this. Let me say that the value of an unit of L over E, so certain S sharp, define the Cartesian divisor of degree 1 on this. I don't want to get into the definition of this notion, but the idea of it,
And it can boundary nice more.
yes. So, okay, how does that go? Maybe that's how the construction goes. So, if you have claim that if I give myself an empty S sharp F, over E, and gives me a map from S sharp to YXE, which corresponds to, at least in the case where, so say F is affinity, then S sharp becomes the form R sharp plus. And what does that mean that I have such a map? It just means that I have a map from the ramified detectors of R plus, was R sharp plus, such that. Okay, so R, sorry, I is automatically invertible in here because R is assumed to be over, R was assumed to live over E, but then we have to enforce the condition that bar phi is constrained, that bar phi, especially our bar phi maps to unit. Again, I'm going to claim that the kernel of this map, which I will call theta, is generated by an element psi, which is a non-zero divisor. And in fact, psi is the primitive of degree 1. So in the linear expansion of psi, and A naught, A1 is the unit in R, and A0 is topological unit. Okay, so
The second condition supposed to correspond to it being kind of like a relative.
Some kind of relative Cartier divisor, relative effective Cartier divisor of degree 1 or S.
Yeah.
Yeah. Yeah, sorry, that's not, yeah. So the formulation is not very good. I tried to kind of see on the board, but I tried to get a maybe last time explain a better formulation. Like there's a way to say it using the environment, which is very clean, but it's not.
So you had this Frobenius operator on YSE. Does it act on Cartier divisors of degree 1 or does it not act on those?
You are thinking about the Frobenius by S?
Yes.
Yeah, so the effect of this Frobenius is that you could turn the isomorphism heuristic by
okay.
Frobenius. Yeah. Yeah, but actually you can still formulate another statement with ST instead of YST by Frobenius. So let's say that S is C, so geometric point, C complete, and algebraically closed.
This map data you have here.
Yeah.
The map is copying still.
Yes. Just because I want to get a map of the places yeah, so this tells you, for example, in the case where S is just with geometric point, that well, in this situation, we are just looking at the example of the one, just the point, just the classical points of this fast content curve for a geometric proof. And so you are just saying that the way, if you want to think about the fast content curve, is that the points, I think the rigid points of the fast content curve, they correspond to projectively up to untilts of C in characteristic 0, so leaving over E up to Frobenius. So the statement may sound a bit confusing after I have taken the existing equivalence to say that like there is a nice projection between perfectly spaces and some characteristic and perfectly spaces and characteristic. But it is because here I have fixed the perfectly space. Then you have to claim that then the system equivalence gives you some equivalence. But here we do not fix any perfectly space. The E is not perfectly space. And so given the perfectly space in characteristic P over Fp, there may be plenty of in characteristics. And in fact, the statement is telling you that the fast content curve is clearly parameterized. Okay, so maybe I take late. I wanted next to discuss the vector bundles on the fast content. Let me finish with it. I will state the main result about them, which is the classification theorem of Fargues content. So what is the vector bundle? As usual, finite locality O module. So for this classification to work, it will be necessary to assume that S is as above the geometric point. In general, there is no classification, but here we will probably do next time explaining how to custom statements to create a. So as I mentioned at the beginning, this is exactly the situation that Fargues contains in the schematic system. So P parity is complete, algebraically closed, non-Archimedean field over the field of P. And there is a way to construct vector bundles on the curve as follows. So I record first definition. Definition of what an isocrystal is. An isocrystal is a pair V by V, where V is a finite dimensional vector space over the field E breadth, which is by definition W OE of F2 bar, and is inverted. It's a finite dimensional vector space over this field. So if you want just the completion of the maximal and harmonic extension E, plus the Frobenius the linear over the Frobenius of E whatever, which is the Frobenius of three vectors induced by the Frobenius phi linear automorphism. So meaning that it's only semi-linear. Because linear is split and then conditions of the and this as a picture they form E linear category. Well, this objects appear in many situations, as theory, many problems in arithmetic geometry, p-adic theory as well, and they are completely understood. So you can actually completely describe categories. This is the whole result of Dieudonné Manine. This category is semi-simple. In fact, it's equivalent to any object is in any isocrystal for E is finite direct sum of. Okay, so you can define what the scope of an isocrystal is, and the category of objects which have a scope lambda is just the same as the category of finite dimensional E vector spaces tensors with a certain object V lambda, which is the unique isocrystal simple of sub lambda. So V lambda, what is it? It has a vector space, so right lambda as E over R, where V and R belong to each other. So it's just R-dimensional vector space over E level. And the matrix of Frobenius is explicitly given by something like this. You have 5 D 0, 0, 0, and then only 0 on the diagonal, and 1, 1 over the diagonal. Okay, the explicit description, but the claim is just that this category is semi-simple. For each rational number lambda, there is a unique simple isocrystal of sub lambda, and its description is explicit description is given as follows. And the endomorphism algebra is the central simple algebra with invariance is exactly the image of lambda in human. So, okay, this is a very explicit category. And now, FQ bar is contained in C. Complete algebraically closed. So, in particular, this means that you have a map from YCE, which was defined using the split vectors, ramified vectors of OC, to spar in and on both you have this Frobenius action. Well, okay, I write what SE to be correct. We want you to remember that S is not just a geometric point. Here you have this action of the Frobenius maximal ramified extensions, which are compatible, are both defined in the same way on these vectors. And so, in particular, what you can do is you can just pull back vector bundles. So, sometimes an isocrystal, another way to think about it is just phi E breve equivalent vector bundle. So, what you can do is you can pull back along this map, and this gives you from the category of isocrystals for E towards Frobenius equivalent vector bundles on Y. But Y was, sorry, X, the Fargues potential was by definition the same thing as the quotient by Frobenius. So in fact, what you get by pullback is just the same as the vector bundle on the Fargues. And this pointer, I will write it like this, E equals so it can be made like, maybe next time I will spend more time discussing some examples of vector bundles, and you see how but it looks like in practice. But for today, I just want to finish by taking the main theorem of Fargues-Scholze, which tells you that in fact this functor is you've got all vector bundles in it. So this functor E is essentially subjective. Well, you can be slightly more precise. So any vector bundle on the curve E on X at E comes equipped with so property you can define the rank, of course, of the vector bundle, but also its degree by first classifying line bundles. So you take the degree of the. So you see that first step is that you classify line bundles in the Fargues-Scholze curve is isomorphic, P curve is isomorphic to. So this gives you a way to this isomorphism gives you a way to define the degree of a line bundle, and in general, it defines the degree of the vector bundle by taking the degree of the power. And once you have this notion of degree and rank, you have and you have for any vector bundle on E on X T, sorry, you have Hard-on-Arrasman situation, so Hard-on-Arrasman theory applied, which is indexed by Q. But of course, for a given vector bundle, there are only finitely many steps with the property that per lambda of E summated of lambda. And for a given lambda, the category of summated of vector of sub lambda in fact just isomorphic to category of isocrystal summated of sub lambda, which has in so before it's a system of high-dimensional E vector spaces. There's only one simple object. And moreover, the Hard-on-Arrasman filtration is fit non-canonically. So concretely, what does that mean? So concretely, that we write OX as E lambda to be the vector bundle attached to the normalization sign to the isocrystal simple of slot minus lambda. And then for the result saying that any E vector bundle can be written as E is direct sum, finite direct sum of finitely many vector bundles, also number. So completely, it's really similar to the description of vector bundles in P1 complex numbers, except that one difference is that now the slopes are indexed by rational numbers instead of class. And I should also warn you that the functor the functor E is far from being fully phased. Lots, if you fix the slope, as I said, the two categories are the same. But there are lots of morphism between vector bundles of different slopes, whereas in this simple category of isocrystals, there were none. So this is a big difference, and this is what makes the vector bundles in the Fargues-Scholze curve. So maybe to finish just an exercise, well, it's exaggerated to call this an exercise, but you can think about it. I wrote down the slogan that the Fargues-Scholze curve behaves like phi E, at least from the arithmetic point of view. And you can try to use this classification. Okay. Use classification. But the fact that HE, the homology of this vector bundle O lambda is 0 always, unless I is 0 if the slope is non-negative, and 0 always unless I is 1 in the case of the slope is negative. So first of all, you have only cohomology in degree 0 and 1. It's another occur. And yeah, if the slope is non-negative, it's always in degree just in degree 0 and in degree 1 is 0. Okay. Again, it's a bit similar to P1, except that for P1 you have O minus 1, which has no cohomology. But anyway, this is something I will discuss more next time. And you can try to combine this to prove that the fundamental group is a fundamental group. Again, when S is just the same as the Galois group. So any finite data cover, that's maybe a better way to say it because it's also technique in this setting. Any finite data cover of the Fargues-Scholze curve, E in fact comes a pullback along the map to spa E from finite data E algebra. So you see, like it's also the same as pi 1 of spec E. It's the sense in which this Fargues-Scholze curve looks like pi E. I mean, and I can say a word about this next week, but you can try to think about it. And maybe start with the case of P1 about the complex numbers. Try to use the classification theorem to show that P1 is still connected. That's a nice example. So the proof of Fargues-Scholze applies there as well, and we're always using Riemann property. Yeah, so
But from what you said, is it here that where the draw is the axis?
no, it's not clear at all, but what is so the fact that the Brouwer group vanishes, the Brouwer group of the curve vanishes is this non-trivial statement. But you can use it to prove that Brouwer group of E is isomorphic to cumulative. Yeah, so argument is as follows: take a central simple algebra over E, put it back with A central simple algebra over E. You just look at, you put it back to the curve, so you look at this. And because the Brouwer group of the curve, so this gives you some Azumaya algebra over the curve, and the Brouwer group of the curve is trivial, so it has to be on the morphism of some vector bundle. But this has sub 0, right? Because it's in vector space as a vector bundle, just in vector space times the structure sheaf. So yeah, so this must necessarily be semi-stable of slope lambda. And you have to use also that this, I guess that this homology group does not vanish, at least for 1 degree. So it must be semi-stable of slope lambda for some given lambda. And well, then it's on the morphism algebra only depends, in fact, on the image of lambda in cumulus. And for semi-stable object, given slopes, categories are equivalent, so you see that we recover. It's compatible with this relation between the crystal and Fargues. So this means that this will imply that A must be on the morphism of the lambda.
Can we use this as the global section of the inside?
Yes, I guess it is. Yeah, you also need. Yeah, so to make the argument, you need to know a little bit of homology of vector bundles. Maybe you need this. You need to know that global sections of the structure sheet are just D also here. Oh, well, no. This correspondence.
Ask. If you look at morphisms between vector bundles of different slopes and take the Galois fixed points, then do you get 0? So like you take Galois fixed points on this category of vector bundles.
Wait, so you want, okay. I'm not sure. No, it's like some huge probability eigenspaces in B plus 3.
Wait, does my question even make sense? What if there's no Galois?
No, that easy to, like, okay, if you assume that C is CP, for example, CP flat.
Yeah.
Then you get an action by familiarity of its vectors, you get action.
Yeah.
But I'm not sure. What I can say maybe related to this question is that Anschütz proved that somehow if you say you can define the far content curve for any F, as I said, on the source of vector bundles for any particular space that is characteristic P. Well, in fact, as I will discuss next time, this is from a stack for the topology and all characteristic space of characteristic P, and you can try to look at its global sections. So in other words, you take limit over all possible complete algebraically closed field of characteristic P. And that category proves to be equivalent to so in some sense, vector bundles on the absolute far content curve, or whatever that means, are just isotropic types.
And not the same as the question I asked.
No, it's not. Well, I thought it was related if you think that the Galois actions come from the Galois actions. Yeah. So the only Galois action that exists here.
So the difference between the completed tensor product of C flat with itself and like the group algebra. Or something like this, yeah.
Yeah, okay, there is this issue, that's right. But
That might be the difference between the question I asked and what you're
that could be, yes.
Yeah, okay.
But it could also be that the space of invariance is 0.
Okay.
Okay, I guess it counts. Like